Hello, AP Chemistry students. Me again, Mrs. Hanson. How are you guys enjoying this unit? Pretty interesting. Lots of plug and chug, lots of math. Anyway, today is going to be super easy. We're going to learn another formula. So you've learned some ways to calculate delta G naught. You can do products minus reactants with delta G of formation values, or you can use this formula, delta H minus T times delta S. Today we have this one, delta G naught, and when I say naught, that's that little standard sign. Delta G naught equals negative RT natural log K. So today the big connection is between the equilibrium constant and delta G naught. All right, well, let's just do an example. So what would happen if you put silver chloride solid in water? So write out the equilibrium reaction. So silver chloride solid, well, that's a classic precipitate, right? But as we talked about, precipitates do dissolve a little bit, okay, and that's an equilibrium system, into Ag plus aqueous and Cl minus aqueous. Okay, so if you remember anything from a couple units ago, this is represented by KSP, the solubility product constant, meaning that this equilibrium does not go very far in the forward direction. We don't produce a lot of Ag plus and Cl minus, but we do produce some. So the precipitate does dissolve a little bit. Okay, and that's called KSP. So let's go ahead and we're going to use this table of delta G of formation values. We'll calculate delta G for this reaction, and then we'll use that to calculate K for this reaction. All right, so you've done this a few times. We're going to do products minus reactants. So we have one Ag plus coming in at 77 kJs per mole. Remember how the moles cancel out, so that's wonderful. And then we had one Cl minus, negative 131 kJs per mole. Okay, so that's my delta G of formation values for my products, and then minus my reactants, which is 1 mole of the AgCl solid. Looks like that. All right, so hopefully you guys are working this out along with me, and we do the products minus reactants for the delta G of formation values, and it comes out to 56 kJs. Okay, and that's, if anything, you could write per mole of complete reaction if you want, or just leave that out entirely, so it's kJs. Notice that delta G is positive because this process is not thermodynamically favorable in the forward direction, and that's that's what we remember from KSP, right? So let's go ahead and calculate KSP. We're going to use this new formula. So the new formula, delta G equals negative RT natural log K. Of course, that's on your equation sheet, so you don't have to memorize it. R is energy R, also on your equation sheet, but it's 8.314 joules per mole per Kelvin. All right, and then your temperature has to be in Kelvin. So on your paper it says at 25 degrees, so we're going to want to convert that to Kelvin, which would be 298 Kelvin. And then natural log and KSP. Okay, and we're going to set that equal to delta G naught. This is about the only way that you can mess this up, is R is in joules and delta G naught is in kJs. So you have to make sure those units are consistent. So I'm going to convert this to joules. How does that look? All right, so now you can crunch the numbers. I'm going to simplify it to this point where it's natural log KSP equals, that simplifies to about negative 22.6. Is that what your calculator is saying? And then how do you get natural log by itself? Of course, you take E to both sides, and then KSP ends up being about 1.5 times 10 to the negative 10th. Now that is a good KSP value because if you remember, the exponents are pretty small. So this reaction does not go very far in the forward direction. So I would say, does the K value you calculate make sense? Yes, because the KSP process is not very favorable in the forward direction. We don't produce a lot of Ag plus and Cl minus from that precipitate. All right, so how does that look? Pretty easy, right? So what that means is that basically you just have a formula that if you have K, you can calculate delta G naught, or vice versa. Now, from that math, we got some really, really common sense connections that if delta G is negative, so the process is thermodynamically favorable, then K will be greater than 1. Okay, mathematically that just has to be true. So if you have whatever your process is, we're going to produce, it's going to favor the forward direction, and we're going to produce lots of products. So we're going to have lots of B, not very much A. K is going to be greater than 1. Delta G is negative. If delta G is positive, that means it's thermodynamically not favorable, okay, in the forward direction, so K is less than 1. So just the opposite, we're going to favor reactants. We're going to favor the backwards reaction. We're going to have a lot of A, and we're not going to make very much B. So this would be things like, of course, KSP, like the example we just did, or Ka, Kb for weak acids and weak bases, right? Their K values are less than 1, small numbers. Okay, so what about delta G not equal 0? So what that would mean is, if you look at our formula, for that to be 0, that would mean that K would have to be 1. Okay, and what that means is that if, that means at standard conditions at 1 atm and 1 molar, we're already at equilibrium. Okay, so there's no reason to go in the forward or the backward direction. We're not driven to do anything. We're already at equilibrium. Okay, so that does happen. A lot of reactions go through a point somewhere at some temperature, okay, where at standard conditions they actually are at equilibrium. Okay, so there you go. So those are sort of your 3 options, all very much common sense, right? The last thing we're going to talk about is, gosh, we keep talking about standard conditions. How often are we actually at standard conditions? So lots of times we're not at 1 atm or a 1 molar solution. So in that case, we have this sort of adjusted delta G formula. So delta G naught, that would be what is the driving force for that reaction to go in the forward or the backward reaction at standard conditions if everything was 1 atm and 1 molar. And then you sort of have this corrective factor that will allow you to say, oh, well, what if I'm actually not at 1 atm, 1 molar? What would be the driving force? What would be the desire to go in the forward or the backward direction? Okay, so for our purposes, we may never actually use this formula. It's been taken off the AP curriculum, but I did want you guys to see it and know that it does exist. The bottom line is that the usefulness of it is we would use it the exact same way we would use Q. So back in the day, if you guys remember, Q is sort of that snapshot of where we are at that moment, and it told us what we were going to do to get to equilibrium. Were we going to go in the forwards direction or the backward direction? We're going to use delta G without the little circle, so I always say delta G not. Okay, in the same way. So just to review, remember Q is the exact same thing as K, just whatever your conditions are at that moment, but it's still calculated as, products over reactants. So if Q is greater than K, then of course you have too much product. Okay, so to get to equilibrium, you'd have to go backwards, right? So delta G would have to be positive because you're going to be driven not to go in the forward direction, but to go in the backward direction. So the process will proceed backwards to reach equilibrium. Okay, so basically Q greater than K and delta G not positive will tell you the same thing, that you're going to go backwards to reach equilibrium. And then, of course, if the opposite is true, is Q is less than K, then that means basically you have too much reactant. Okay, so delta G will be negative because if you have too much reactant, you want to go forward to get to equilibrium, so the process will proceed forward to reach equilibrium. So we may or may not see that, but at least you kind of have a glimmer that it does exist. Okay, it's always more to learn. That's it. I told you it was a pretty short video, so you got another tool in your tool belt, another formula you can use. Just be really mindful of the units. Make sure everything's in KJs or make sure everything's in Js. All right, thanks for listening. Have a great day.